last topic for this term, that is your sound. Okay, so which the chapter is in page number 123. Okay, the chapter starts at page number 123 and the chapter's name is sound. Now what is sound? So as I speak, you all can hear me, isn't it? So you can hear the birds chirping around, you can hear many things around unless and until your ear is functioning well, isn't it? So as long as your ear functions well, okay, you can be able to hear every sound. So how is sound produced? Sound is produced by the vibration of the particle. So if there's any vibration, or if there's any movement of the particles, sound is produced. Okay, and there should be a medium to carry the sound. So we'll get into details about it. So first, let us understand how is sound produced. So sound is produced by vibration of particle. So anything that vibrates produces sound. For example, this one here. It was lying on the table, it did not produce any sound. Okay, no sound was heard from it. But if I do this on the desk, what did you hear? Sound. Okay, and why did you hear the sound? Because this scale, okay, the stick, when touched the desk, okay, it vibrated. So what happened? The particles vibrated, and when the particles vibrate, sound is produced. So every time there is vibration, sound is produced. Okay, even the cell phones. How do they produce sound? When the cell phones vibrate. Okay, so sound is produced by the vibrations of particles. And now, first one was, how is sound produced? Sound is produced by the vibration. Okay, sound is produced by the vibration of particle. Now, second important thing, sound requires a medium to travel. Okay, so sound cannot be heard in vacuum. Sound requires a medium to travel. And that is why the astronauts, okay, on the moon, they have a special device. They use a special device to communicate on the moon, because there is no medium on the moon to let the sound travel. Okay, so sound requires a medium to travel. Say in vacuum, you take a jar. Okay, you take a jar and then you put your cell phone inside the jar. Okay, now what you have to do is you call your phone, you call at your number, and the phone will start ringing. You can hear the sound even though the cell phone is inside the jar. You can hear the sound of your ringtone, isn't it? Of the phone ringing. But then what you have to do is you remove the air, okay, make it vacuum. Now when you remove the air, if you remove the air from the jar, so it is complete vacuum. There is no air inside the jar. So now you ring your phone again, okay, you call your phone again. So what will happen? You see the phone vibrating, but you will not hear the sound. Okay, you can see the phone vibrating, but you will not hear the sound. What does it mean? It means that sound requires a medium to travel. If there is no medium, you will not be able to hear the sound. So this is what it means. Sound requires a medium to travel or to propagate. Propagate means to travel. Okay, sound needs a medium for its propagation. It cannot travel in vacuum. This is why two persons cannot hear each other on the moon or in space where there is no atmosphere. Sound can travel in solids, in liquids as well in gases. So sound can travel in all the three states of matter: solid, liquid and gases. Well, the speed of sound is highest, maximum in solids, least in gases. Okay, now why is it maximum in solids and why is it least in gases? Because of their molecular arrangement. Okay, solids, now look at this, solids, the particles of solids are tightly packed. So, the particles of solids are tightly packed. So, if one particle starts vibrating, okay, if somebody speaks or a sound, if one particle starts vibrating, it will touch the other particle. This will also start vibrating and this will touch the other particle. Since they are very close to each other, it becomes the sound travels, it becomes easier for the sound to travel because the particles are closer to each other. In case of solids, the particles are tightly packed. Okay, that's why it becomes easier for the particles to travel. Now, in case of liquids, the speed of the sound becomes little bit lesser because the particles are far apart. So they take time. When they vibrate, okay, they need lots of energy to vibrate, and when they vibrate, they touch the other particle. Okay, so therefore, in solids, the speed of sound is maximum. In liquids, it is comparatively smaller, lesser, and in gases, since the particles are very much far apart, okay, so the particles need a lot of energy to vibrate and to touch the other particle, and thus speed of sound is maximum in solids, okay, lesser in liquids, and least in gases. So that's why if you put your ear on this desk and if one of your friends taps it from the other end, you will immediately hear the sound because sound travels fastest in solids. Okay. It's mentioned over here the speed of sound in iron is nearly 5,000 meters per second. That means in 1 second, the sound can travel 5,000 meters in iron because the particles are tightly packed. Whereas in case of water, it is 1500 meters per second, which is lesser compared to iron. So water represents liquid, and the speed of sound in water is 1500 meters per second, which means in 1 second the sound travels 1500 meters. And in air, the speed of sound is 330 meters per second. It means in 1 second it travels 330 meters. And all this variation of speed is because of the molecular arrangement of solids, liquids, and gases. Okay. So when our body vibrates, the particles of the medium also starts vibrating. During vibration, the kinetic energy of the particle increases and it changes into potential energy and potential energy into kinetic energy. And this is why sound is a form of energy. So sound is a form of energy because there is a change of energy. You know, when particles vibrate, they gain kinetic energy. They start vibrating faster, isn't it? And when they vibrate faster, it means kinetic energy is a form of energy. And that is why sound energy is also a form of energy. Okay, and now propagation of sound in air. Sound propagates in the form of wave. Okay, sound travels, propagates means travels, sound travels in the form of wave. And there, before we move on to the how sound travels, let us discuss the types of waves. So there are two types of waves in which sound and light travels. Okay. So they travel in the form of waves, and the types of waves that we are going to discuss are, there are two types of waves. One is your longitudinal wave. The another one is your transverse wave. Okay. Now longitudinal wave travels. Okay, what is longitudinal wave means? When the particles travel to and fro. Okay, what does longitudinal wave means? It means when the particles travel to and fro, like a swing. You know how swing moves, right? You go forward, you come backward. You go forward, you come backward. The same way, in longitudinal wave, the particles move to and fro. They go forward, they come back. Forward and back. Okay. In longitudinal wave, the particles vibrate to and fro. So they flow with they go in the direction of the sound. Okay, to and fro means they go in the direction of the sound. Okay. And in transverse wave, the particle moves up and down, like the waves of the ocean. You've seen those waves of the ocean. It goes up and down. Okay, up and down. The same way, transverse wave also. In the transverse wave, the particles move up and down. Okay. So this is one difference between longitudinal wave and transverse wave. In longitudinal wave, the particles vibrate to and fro. In transverse wave, the particles move up and down. Okay, they vibrate up and down. Whereas in longitudinal wave, the particles vibrate to and fro. Okay, so another one is, see, this is how longitudinal wave particle travels. See, the particles are here and sound is produced from here. Okay, when the sound is produced, what happens? The particles, the particles which are closer to the sound, they get disturbed. So they are moved forward. Okay, they get disturbed and they move forward, and they just come closer. And once they come closer, when they have touched other particles, they can move back. They come back to their normal position. Again, a set of them come closer. So when a group of them are pushed together, they come closer and they get back to their normal position. Another set is pushed together, they come back to their position, and then another set would be pushed together. They come to closer, they move back. So a series of what happens when they come together, we call it compression. Okay. When the particles they move together, when they come together, we call it compression. And when they are in a normal position, we call it rarefaction. When the particles are there in their normal position, we call it rarefaction. And when the particles, when they come closer, we call it compression. So longitudinal wave comprises of series of compression and rarefaction. Okay, like those springs, the long springs when you do it. So you push it, or the slinkies where you play. So when you push it, a bunch of the strings they come together and then they come back to the normal position. Again, another set comes closer and they come back to the normal position. So it's like playing with a spring. Okay. So this is your longitudinal wave. It comprises of series of compression and rarefaction. Whereas the transverse wave comprises of, as I told you, it moves up and down like the waves. So it comprises of, when it goes up, we call it crest. Okay, when the particles go up, we call it crest. And when it goes down, we call it trough. Okay, so the transverse wave comprises of crest and trough. Crest and trough. So when it goes up, it's called crest. When it goes down, it is called trough. So crest and trough makes transverse wave, and longitudinal wave comprises of rarefaction and compression. Okay. And the third one is in longitudinal wave, sound travels in the form of a longitudinal wave. Sound travels in the form of longitudinal wave. It goes forward, comes back. This is how sound is produced. The particles move forward, goes back, forward, back. And light, represents transverse wave. So the light, they travels up and down. The particles of light, they travels up and down. So these are the differences between longitudinal wave and transverse wave. Okay. So there are two types of waves in which the particles travel. One is your longitudinal wave, the other is your transverse wave. In longitudinal wave, the particles vibrate to and fro like a swing. Okay, they move forward and then they come closer to another set of particles. Once they have touched the other particle, they move back to their normal position. This set of particles which have been touched moves forward and touches the other particles. And then after touching the other particle, they come back. Okay, and in this series they vibrate. This is how they vibrate, to and fro. Whereas transverse wave, in transverse wave, the particles they vibrate up and down. Okay, up and down, like the bouncing of the balls. Okay, up and down, like the waves of the ocean. And longitudinal wave, as I said, the particles when they come closer, it's called compression. And when they get back to the normal position, we call it rarefaction. So longitudinal wave comprises of a series of compression and rarefaction, whereas a transverse wave comprises of a series of crest and trough. So crest means when the particles vibrate up, and trough means when the particles vibrate down. Okay, crest and trough. These are the differences between transverse wave and longitudinal wave. And in the next class we will continue with how sound propagates in air, how sound is traveled from the source to the listener. Okay, so till here we'll complete till here. We'll see you in the next class. Thank you and have a good day.